thank you very much for making the time to come to the department today. For those of you who are visitors to Cambridge and to this event, a very, very warm welcome. To many of those of you who have visited before or are local, welcome back. It's very nice to spend what has turned out to be a rather cool and wet day outside to come into this great department and sort of warm the mind, to sort of listen and actually do science. We're very, very proud that this department is considered one of the world's great chemistry departments. And in the lecture that you'll hear in a moment, you'll see why we command that reputation. This is an important event for us because it's a way that we show you, the taxpayers, and the young people in the audience who are going to play an important role in shaping the world in which we live, why what we do here is important and the people who do the science. It'll be an extraordinary privilege to have Professor Erwin Reisner talk about the work that he's doing. This stuff is impressive, okay? What he and his team are doing is going to truly transform an important part of the way in which we live. Very often we use words like inspiration, transformative, impactful. If I use those words in my introduction, then there's justification why we do so. Now, Professor Reisner has been awarded a number of eminent prizes. He holds a professorship from the Institute of Engineering, which is one hell of an achievement in the chemistry department, which recognizes the work that an individual does across disciplines. His team has spent a very busy week setting up experiments that you'll see around the building and displays at the front. So this is science that takes chemistry and puts it into and applies it in ways that are going to change the way we look at energy, the way we create energy, the circular economy. And the presentation is something that I'm sure, having heard it a number of times, you'll be talking about in the next couple of days and you'll be telling your friends about. And I guarantee that has been the case over the past year, where it's been covered in international news outlets around the world. This science, his group, you'll be hearing about in the years ahead. So it's great to have you here. It's really fantastic to have Erwin, a wonderful colleague, a really sort of successful group. And I think what you'll get across, not enthusiasm about the science that's done, but a bit the day after a great football victory for England, right? Science is a bit like sport. You require a manager to attract talent, to have vision, to put the right play into action in order to get great results. And Erwin is a sort of manager of a fantastic team of incredibly talented people who are inspired to do great science. We're very proud of the work they do. If you haven't, after the lecture, seen a lot of the sort of displays around the building and the experiments his group has set up, please do so. But we're really pleased to see you here today. If you've just arrived, make sure you walk around the building. There's really exciting things to do. If you've already done some of the experiments, look at your map and see what's left. But enjoy the rest of the day, and I'm sure at the end, Erwin, you'll be very happy to take some questions. Right?
Absolutely.
Great. Thank you.
Also, welcome from my side to the Yusuf Hamid Department of Chemistry. It's a real pleasure for me to be here and to communicate with you. It's truly one of the highlights of my year. So after the lecture, feel free to come to me afterwards. I will also be at the device displays. I'm happy to take any questions just right after the lectures, or also more informally afterwards outside. What I would like to convey to you today is really that chemistry is a phenomenal discipline, and I think it's really at the very core for us to meet some of the most difficult and contemporary challenges, in particular when it comes to sustainability. So when I started studying chemistry, the reputation of chemistry was not a great one. It was very much associated with pollution, with ozone layers, etc. But today I think this has really shifted, or it should better shift, because there's a lot of things we need to tackle where we will need chemists. So for the very young audience members, consider chemistry as a career. For those of you who are chemists, you've made a good choice. For those of you who have not studied chemistry, you're also most welcome, and of course to embrace chemistry in your future. And I would like to do this by essentially explaining our research. And with our research, I really mean my laboratory, my team's research. Chemistry today is a team effort. I'm very pleased to have a phenomenal team of PhD students and postdocs. It's extremely diverse. My members come from all over the world, from many different backgrounds, and it's very nice to see them getting on with research. And if you've seen from the videos, our science is not only in the lab. We like to take it outside, and we would really like to make a difference to the upcoming challenges. So what you can see here is really a glimpse of one of such devices, a floating solar panel that does some chemistry, but I will come back to this later. First, I'd really like to introduce the challenge and this huge opportunity that chemistry has today. As you will be aware, our world is powered by fossil fuels. effectively by coal, gas, and oil. And you can see here the scale. This is global energy consumption in 1,000 terawatt hours. And effectively, since the Industrial Revolution, of course, launched by Britain, this has been increasing tremendously. And today, we should really remember that about 75% of all our energy is fossil derived. So we're actually very far away to defossilize our economy. But of course, we know that's needed to avoid environmental consequences from excessive carbon dioxide emissions. But what's the projections? And those are actually very bright. If you look at effectively the transition scenario, this is admittedly an optimistic scenario, you will see that there will be a dramatic shift coming upon us. And I really think we need to embrace this. It's a great opportunity, and the country or society that drives the transition will really be in the leading position in the future. And as you can see from this plot here, that's a fairly recent one, it's all going to be about solar. So solar energy, even in Britain, will be really transformative. And you can see in about 1 or 2 or 3 decades, effectively, from the energy consumption level, this will be replaced by solar. Of course, wind will have a very significant contribution as well, significantly in Scotland, Denmark, other countries, and the rest then is the chemical industry that I will be talking about today. And I think this is not something that should be shied away. I think it's great that this happens now at this stage of time. So why has there been such a dramatic change in solar, or why is there such a prediction in change of solar? And it's a lot to do with prices, of course. So when I started my research group in 2009, the case for solar was not a particularly attractive one. So in fact, if you look at the cost of energy that's expressed here as levelized cost of energy in US dollars per megawatt hour, which is the cost if you were to build a new plant running until the end of the lifetime, and the cost of the electricity you produce, then you will see photovoltaics looked pretty poorly. It was about $360 per megawatt hours. The others, the fossils and wind, were all mixed bag, quite similar, but surely much, much cheaper than solar. When I talked to my colleagues here in the physics department or the Cavendish when I arrived, even they were quite pessimistic about the midterm future of really PV being competitive without heavy subsidy. But while the fossil fuels are roughly unchanged in terms of cost, wind, of course, came down, solar really, really came down tremendously. So this, of course, are global prices. And today, in many locations, solar energy, if you take away subsidy, is actually the cheapest form of energy. And that's a consequence of the economy of scale. There's very heavy mass manufacturing now, in particular in China, but this really has driven down the prices, and there's no real reason why these prices should not drop further. And that's the consequences, this mass rollout of solar in the future. It does not even make economic sense anymore to build fossil fuel powered plants. And that's exciting. So this means a lot of the future growth could then also be driven by chemistry, which means as we start reaching peak electricity production, there's enough electricity produced from solar, we will need to think how to replace the 75% fossil fuels of a good chunk which goes really into the chemical industry. And that's one of the challenges we are really addressing here in the research group. And this plot, I think, shows this timeliness of chemistry very well when it comes to commercial opportunities. So what you can see here is a timeline that goes from 1990 to 2050, and the transition of different sectors from essentially still a fossil sector to a renewable sector. And you can see this, of course, color-coded. So if we take electricity production, the easiest to produce renewably, you can see that we are quite far advanced. In 2025, we are already moving from mass to late market, because these wind turbines, these photovoltaic installations exist. It just needs now really to take over. And we will saturate electricity production in most parts of the world quite soon with renewables, which is the green color. Light road transport. This could, for example, include electrified vehicles. So BYD Tesla cars, for example. If you go back 10 years ago, it was still extremely rare to see electric vehicles on the road, at least in the UK. And that's why in this time here as well, this was still solution development, and EV vehicles just moved into the niche market. But really today, you can see there has now been an excessive or very fast rollout. We are now already in mass market production, so it's quite mature, and there are very strong renewable incumbents already in the field. So if you want to build from a startup a better electric vehicle company, you better have a very, very good idea. It's going to be very challenging. But if we fast forward, go now to the chemical sector, this is still at quite an early stage to transition from a fossil-powered industry to a really sustainable industry. You can in fact see this tipping point for chemistry is only predicted to start in the 2030s, because we still do not have at scale and the vast diversity of chemical reactions we have to run, good solutions to power those sustainably. But this will ultimately be really, really required to defossilize and to deal with climate change. And this is really a challenge where I think a chemist is phenomenally well placed to attack this problem, or a chemical engineer, of course in collaboration with many, many other disciplines. And that's really what we are interested in. Can we make chemicals sustainably? Can we make trucks sustainably? Can we make fuels sustainably? And that's what we try to do in our chemistry, and of course, using solar energy. And for the first 10 years, when I started my research group, this was really very basic science. We just started to troubleshoot individual parts of the process. How can you capture solar energy? How can you extract some of this energy similar to a photovoltaic panel? How can you use this electricity or energy to drive a catalyst? But it really took us 10, 12 years to build the first small prototypes to make this happening. And now it's, of course, a very exciting time for us because we can build up on those early results and hopefully translate this into the real world. And what I'm very excited about is that there's quite a good number of students leaving my research group as well. So they're alumni, and they also all start, or many of those also start startup companies. So there are about 7 to 8 startup companies already co-founded by members of my team who left. And here just 4 of those, and all of those are in the business of using carbon dioxide, biomass, and plastics, and upcycle those to useful products. And that's just one example. That's the first pair from my laboratory who left and co-founded a startup. Diocycle is the name of the startup. So this is David Wakerly and Sarah Lamerson. And the gentleman in the middle is not an alumni from a research group. This is Bill Gates for the younger audience. And they're already very successful. So they have funding from Gates and also have a startup quite significantly with about 40 to 50 people in several locations around the world. So it is really, for chemistry students, a very exciting time because it allows you to be extremely entrepreneurial with a lot of opportunities. So what do we need to do? It actually can be summarized on one PowerPoint slide. If we look at today's chemical industry, how we build it, it is all constructed from fossil fuels, our main resource. The fossil fuels provide us with the energy and the carbon. And all we do with the energy provided by the fossils, we rearrange the carbon atoms and we get different kind of products or other atoms like nitrogen. And what we do in the first step is actually only prepare a couple of handful of basic chemicals, the basic building blocks from where we build everything else. This would be ammonia, syngas, ethylene, and aromatics, for example. And from there, we make all the products we use, like, say, fertilizer, kerosene, plastics, fibers, chemicals, of course, for all the uses in our daily lives. And just to illustrate one example, which should hopefully show that it's so difficult to move away from fossil fuels. Ammonia, 50% of global ammonia production actually goes, 50% of global fertilizer production, no, that's incorrect, sorry, 50% of food production is only enabled thanks to fossil fuels. And that's because we produce fertilizer that's made from fossil fuels. We take fossil fuels, in steam reforming we make hydrogen. This hydrogen we combine with nitrogen in the Haber-Bosch process to make fertilizer to create the food. If you would take away this fossil-derived fertilizer production, we will have mass starvation on the globe and could not feed half of the global population. This, of course, makes it immensely difficult to start moving away from fossils, but we have to get the process started. And of course, the same is true for all of those as well. We cannot really have kerosene at the moment without fossil fuels. So what could we do? We need to find a replacement for fossil fuels to effectively build again our basic chemicals to create the products for our daily lives. We do not want to give away or give up on the standard of living we have. If anything, we want to expand it, but we need to rebuild in a different and a more sustainable way. And it's quite interesting because we actually know what these sustainable resources are supposed to be. There's quite some analysis from the German Academy of Engineering, from the Royal Society in the UK, and they all, at least in Europe, come to the same conclusion. There are 3 ingredients to build the organic chemistry of the post-fossil age. And those ingredients are carbon dioxide. So everything we emit at the moment, we better capture because it will be a useful resource in the future. About 30% biomass. This is mainly lignocellulose, wood, etc. we accumulate, and plastics. And plastics in this case should already be circular plastics, so not fossil-derived plastics, but actually green plastics. And it's because it's not easy to make something from carbon dioxide, we will need additional energy input, and this energy can be provided by the sun. And this is really summarizes what my laboratory is doing. We use solar energy to convert carbon dioxide, biomass, and plastics into something useful to essentially replace fossil fuels in the future to build a new type of economy, a sustainable circular economy. And in a bit simplified version, we can also deploy this close to the chemistry department. So if you walked into the department here, we're just in the lecture room, you will have seen there's a little car park. I'm a big advocate that we should replace this car park by some solar panels that can do some of this chemistry I was been talking about. And the vision is really then using sunlight with our ingredients of water, waste, and air, convert them into useful products. And the type of products I'm talking about really is something like synthetic fuels. This can be something more simple like hydrogen. It can also be kerosene or alcohols. We can make chemicals from methanol, pharma products. I mentioned drug production already. Green sustainable plastics, and of course also fertilizer, steel, and anything we need for our construction industry. In principle, we can do all of this sustainable. We just have to develop the catalysts and optimize such processes. This also, with synthetic fuels, allows us to deal with chemical energy storage. Batteries are great, but of course the capacity you have in batteries is limited, and they're not very good for seasonal energy storage or long transport ways. So for heavy-duty trucks, for example, still fuels will be preferred. If you need to store energy from summer to winter, also chemical fuels have big advantages, or aviation industry. And then, of course, the transportation sector. So this should give a bit of a summary what we could do and how we envision a circular chemistry department. I will then show you at the end of this lecture as well. So our largest reactor built to date is actually shown on this picture. It's also in the foyer for you to have a look afterwards. This was primarily built by Arifin. He also, Motia was part of some of the experiments. And you can very easily see who really only joined this for a picture. Surely the guy with the sunglasses just had a quick look and was very proud of his PhD students. And this is quite a nice achievement because this is truly a 1 square meter reactor. So for instance, it was a huge milestone of going from the laboratory, where we often deal with millimeter or centimeter scale, to have something that's really tangible and where we can make significant amount of products. So in this particular case, you can see this iPhone from Arifin. He's actually filming this here, what's happening. And when you shine light, you can really see this formation of hydrogen bubbles. I will show you later what exactly we are doing in here. But for now, we are just converting waste into hydrogen in these reactors. And I think that's actually very exciting. And then we just collect it up here. And then we want to just demonstrate we can use it in a fuel cell or do some green chemistry with this hydrogen. There's one issue with this picture that's not maybe most fitting for the chemistry we are doing. So I've just rebranded this here as a Solar Chemical Technologies Institute that hopefully it will be forthcoming soon. So this picture should just show you a couple of little examples of how we got to these large-scale reactors. I do not want to give the impression this can be done overnight, or this is actually a year's kind of work. It really took us 15 years. This was our very first reactor. This has little electrodes. They are 1 square centimeter in size. This lasted about half an hour, and then it fell apart, and we could just measure some trace amounts of hydrogen. But it was a fantastic starting point. At least it worked a little bit. Academically exciting, but really only for us, I guess, in this case. But over time, we have just looked at many different device configurations. All of these are fundamentally different. I will not go into any detail. Again, for the interested people, I'm happy to discuss at the display cabinet. But you can see we use 3D printing, we use gas-tight reactors, and we also have some different device configuration for testing. And at the moment, we do this quite routinely, that we look at many different deployment scenarios of those type of reactors. And you can see this here is already actually floating. Oh, I'll come to this in a moment, sorry. So this is actually the display cabinet where you can see all of those devices. And that's a larger reactor I will also show you in a moment. And the last device I had just pointed to, you could see it floats on top of water. And this was because it was possible to make extremely thin little solar panel that do this chemistry. And they were so thin and lightweight that they can just levitate in an aqueous solution. So what we did here, we took it outside on the River Cam. For those of you who are not from Cambridge, that's the Bridge of Sighs from St. John's College. And we just put it into a little plastic bag that we filled with a bit of water and saturated with carbon dioxide. And we could just let this float on the water for a day, and it really produced a milliliter or so of syngas. And syngas is a synthetic, very useful fuel. So it really made something very useful. And the syngas, for example, can be used to make kerosene. Again, this will not change the world. It's just a demonstration what we can do. And we can actually do things in very different locations. When it comes to solar energy, intuitively, we would think of land application. And then we always struggle, where does all this land come from? And there's always competition with farming and solar installations, but actually we have to be more creative, right? We can even go actually on open water bodies. There are also limitations. I will not say that's the end solution, but at least it provides new opportunities. And especially as sea levels increase, this provides future prospects for the chemistry department as well. We should point out that Cambridge is about 6 meters above sea level. So when the car park is no more, of course, there can be a Cambridge by the sea, and this allows us to produce fuels here, irrespective of what happens really with car parks or port deployment scenarios. So one of our larger reactors we built, this has been shown just in the video before Nick introduced before this lecture, was this 0.35 square meter reactor, and that's our largest reactor to date that can really convert carbon dioxide into a synthetic fuel. And this was a massive team effort. This was a part of a collaboration between my team, this is Virgil Andre and Motia Rahman, and the group of Professor Sam Strength from Chemical Engineering with his postdoc and PhDs Miguel and Yu Xian. And it took us about 3 months of 5 people working full-time to actually develop this type of prototype device. And these are 100 little leaves, and we call them artificial leaves because they really function and actually behave and look like a real leaf. So what does a leaf do? It takes carbon dioxide, water, together with sunlight to make sugar and oxygen. These leaves do exactly the same, but instead of making sugar, we make a useful fuel. That's why this field is also called artificial photosynthesis, and we make artificial leaves to build artificial trees, etc. So it's highly bio-inspired. And this was a Herculean effort, not only so to build this device. I've mentioned it took 5 postdocs a couple of months. Only just fabrication costs and materials costs about 40,000 pounds. And then the most difficult part was actually to get it through the channel. This was just post-Brexit, and to bring it to this competition site in Italy, in Ispra. And the competition was in Ispra because it was funded by the European Union, and Ispra is the European Union solar testing facility. So you have everything certified, standardized. It's just the ideal location. And of course, it's in Italy. If you do solar energy conversion, you want to be in Italy in summer. Makes a lot of sense. So we rented a car, we put it all in the trunk. I'm sure all the safety forms were duly completed for this. We made it through the tunnel, and then we arrived very happily as a team in Italy here as well. And this here again is the official picture from the competition we used. Bright blue sky, as you would expect. And in fact, in preparation for this competition, we did quite a lot of real-world testing, just on a smaller scale. We built some reactors and always waited that the sun comes out, and of course tested it on our rooftop of the chemistry department, rooftop of the physics department, and it really worked quite well. So we could really predict how much syngas we would produce in the competition, and we were very enthusiastic and optimistic about all of this. But the real pictures from the competition were actually this. So this is day 1 of the competition. This was essentially a competition where we had to start at 9 a.m. on this Monday morning, so there was no possibility to postpone. And this is how our device looked like after a couple of hours. So it was not this bright day that one may expect in July in Italy. And this was then in the afternoon. Actually a thunderstorm coming down. And in this afternoon, 1/4 of the annual rainfall came down in Ispra Italy. So it was probably the worst day in the year you could have done any solar chemistry or solar powered devices. And that essentially was the device. And then we had a huge problem because we did not have sunlight. The device did not really properly function, because how this device works is you shine light and you make this syngas, so you produce a gas. And this gas creates a pressure. And with this pressure, we would just collect our product in this tank. And for the chemists in the audience, this tank contains potassium hydroxide, so it's quite alkaline and corrosive, and it would just capture all the unreacted carbon dioxide, and the syngas would just accumulate here. That's what we wanted to demonstrate. But because there was no sunlight, there was no overpressure, and actually we created some underpressure in the device. And underpressure meant that our highly alkaline corrosive solution was just pushed back into our device, and our device does not like corrosive solutions. So this is a picture of the device just before we started, and this was after 1 day. And yellow is good, and copper, etc., is bad. So essentially just one of our light absorbers, one of our key components of this device just dissolved, unfortunately, in these highly corrosive conditions. So actually we were the only team that had a device that did what the competition was all about, to demonstrate direct conversion of carbon dioxide into a product using solar energy. But because, of course, we broke the device, it was quite difficult to give us the first prize, but nevertheless we got second prize. The trophy you can inspect also in the display cabinet outside. But if you look at the faces, yes, I think we were okay, happy, but not really enthusiastic. And we were not so enthusiastic is because there really was no check associated with the second prize. And what do you think the first prize would have been of this competition? Well, some of you will have seen already in the video that played before. 5 million euros. So character building, I think, is the answer. That's what we tell our early PhD students. It's probably good, because that's also why I'm still standing here in front of you and not early retired on some nice island elsewhere. And we keep pushing, and here in 6-7 years there will be another competition. So we will be back, and we make sure we put in a proper tight valve to not dissolve our device again. Okay, I've talked quite a lot. I will just show one video that was produced by a PhD student and a postdoc that explains the research and the field in more general ways. And it's known by us as the Lego movie.
Welcome to Bricktown Land, a model of everyday society. The people here are active all through the day and all through the night. Everyone's constantly in motion, and this requires a lot of fuel. For example, fuel is needed for their cars and their planes. Fuel is a store of chemical energy which keeps society moving. Even the people run on fuel. Food is like fuel for humans. But what does a fuel look like? Well, probably something like this. It's a long chain of carbon atoms. When these atoms come into contact with oxygen and are given a push, a huge amount of energy is released. And also the byproducts, carbon dioxide and water. This is how a fuel works. This could be visualized as a ball on top of a hill. The fuel starts in a stable state, it's given a push, and energy is released, forming the byproducts. The difference in energy between the starting material and the byproducts is used by the people of Bricktown to power their society. But there's a huge problem on the horizon for the people of Bricktown. Lego oil, which is used to make Lego fuel, is running out. And what's much worse, burning Lego fuel is releasing Lego carbon dioxide into the atmosphere, which is causing Lego global warming, leading to wild and unpredictable weather conditions. To solve this problem, people turned to the Bricktown scientists, who were tasked with solving the energy crisis. The scientists' first idea was to use solar panels instead of fuel. Solar panels convert the energy we get from the sun into electricity, and can power anything as long as the sun is shining. The problem is, as soon as the sun goes down, everything stops working. The scientist's second idea was to use solar panels to charge batteries.
Get your batteries here.
Batteries are a great way to store energy and are perfect for small-scale electronics, such as mobile phones, or if you're from the 90s, Nintendo Game Boys. Battery technology is constantly improving, but still they're too heavy for some large applications, such as powering aeroplanes. So is there any way that people could just make more fuel? One idea was to make more oil by building a time machine and using it to go back in time in order to kill more dinosaurs. Then they could be buried underground, and in the future there'd be plenty more oil to go around to power society. Attempts to build a working time machine were unsuccessful, however. It turns out that it's a very complicated concept, and it was just a stupid idea. I'm pretty sure someone was fired for that one. But their final idea was much more sensible. What if we can take the byproducts of burning fuel, carbon dioxide and water, give them some energy, and turn them back into fuel, thus creating this renewable energy cycle? It would just be like pushing the ball back up the hill. It sounds simple, but right now the people of Bricktown can't do this. But plants have been doing this process all along and just didn't tell anyone. Plants can use the sun's energy to turn carbon dioxide and water into oxygen and sugar, i.e. fuel. This is called photosynthesis. The people then tried to interrogate the plants into revealing the secrets behind this process. How'd you do it? You better tell us, or we'll feed you to the horse. This obviously didn't work, so instead the people chose to study photosynthesis scientifically. Now the people of Bricktown Land work on a concept called artificial photosynthesis, and the scientists are trying to develop a material that can turn carbon dioxide and water into fuel. This is actually the same goal as a number of human scientists. Researchers in the Reisner laboratory at the University of Cambridge, as well as a number of other scientists around the world, are working on a way to make renewable and sustainable fuel that might be used to power our society in the not-so-distant future.
Oh, no. I don't think you can try. So you may have recognized one of the two co-producers was the person also who co-founded this Diocycle startup, who was next to the picture with Bill Gates. This movie in particular, it was 11,000 pictures in the stop motion. So it took them a couple of, well, more than a year actually to collect everything and put it together. And he also did a fantastic work in his PhD on top of that. So far it was on the theme of using carbon dioxide and make something useful out of carbon dioxide. I would like now to go more into more classical solid waste conversion, in particular using biomass and plastic. And with biomass, again, I would just like to emphasize that we're interested in lignocellulosic plastic that is not in competition with food production. I think it's a very important aspect of what kind of biomass we use. And in a way, this reminds me of Back to the Future, where you can also just put some waste into Mr. Fusion and create energy. Of course, we don't want to do cold fusion. We also hope our technology works better than cold fusion. But from a concept, it's all about extracting energy from waste. And it's very interesting. Some of you may recognize Michael J. Fox here at the back. Michael J. Fox is actually a significant funder of activities in this department for Alzheimer research. So it's also an interesting aspect here. So how does it work? And this was quite an incidental discovery in my laboratory now about in 2017. And we found if you do something very simple, you can actually do some quite interesting chemistry. So what you see here is a large image of a test tube that has a little piece of wood. And then we have inside here a yellow solution. That's the catalysts we make in our laboratory. So the catalyst accelerates a chemical reaction. And these catalysts are photocatalysts, so they're driven by light. So these catalysts take up the energy from sunlight in this case, and then they start doing something with the piece of wood. And what they're doing is they're essentially degrading it, decomposing it. Just looking for my Here it is. They're degrading it, and you can see that there are bubbles emerging, and these bubbles are clean hydrogen. So we are converting with solar energy in our photocatalyst this wood into clean hydrogen, and we also accumulate quite interesting chemicals here in solution, which of course you cannot see. There's all sorts of organic acids that can also be useful, again, for rebuilding this chemical industry, hopefully in the future. And biomass and wood, of course, is great because we have so much of it, so we can in principle make significant quantities of product as well. Something almost identical works with plastics. So in this case, shame on me, I have a plastic bottle here. What you can see here is just a piece of a commercial PET water bottle, and we just coat this with our catalyst. And again here, when you just shine light, simulated solar light in this case, you again get this hydrogen. So we can just make hydrogen from this plastic bottle using our catalysts. And this was extremely exciting to us because it's such a simple system. 4 ingredients, light, photocatalyst, water, and waste. And you get interesting products. We immediately started to scale this up a little bit. This is one of our early reactors where we converted using solar energy textiles. So in this case, we were interested in fast fashion industry, for example, all this waste that's being accumulated, and we could show actually this fast fashion polyesters, for example, can just be degraded here to make hydrogen that can be used. Important to us is not only that our chemistry is sustainable, also the materials we use should be sustainable. And in this particular case, I'd like to show you that we can make these photocatalysts also from waste. So in this case, we can just take 100 grams of cellulose, which is a component of biomass, put it in a furnace, and what we produce is about 50 grams of these photocatalysts. So we can make our catalysts from waste, and these waste-derived catalysts can then convert waste further into hydrogen, organic chemicals, etc. So it's a very sustainable process in terms of chemistry and also the materials we are using. And also here a quick movie that illustrates actually how this really works.
Everyone seems to have a love-hate relationship with plastic. It's so versatile, we use it for everything. But once we throw it away, it pollutes and endangers our environment, the oceans, animals, and our general health. Scientists estimate that by 2050, there will be more plastic in the oceans than fish. So should we stop producing plastic? What if we could recycle it into a new, useful product, a carbon-free source of energy? This is what Professor Reisner's group works on as part of the Creative Circular Plastics Center in Cambridge. At the end of its life cycle, we want to transform plastic into hydrogen fuel. Hydrogen fuel is cleaner than oil-based fuel because it only releases water when burnt. No carbon dioxide. Basically, this is how it works. We put the waste in a water solution, add a non-toxic photocatalyst, and let it sit under the sunlight. After several days, the waste breaks down into other useful chemicals and also forms hydrogen bubbles. This process is called photoreforming. It's clean and allows for all sorts of waste to be recycled, such as food waste and cardboard as well. We've already produced enough hydrogen to power a phone for 40 seconds. And we hope that in 5 years from now, you'll be able to make use of your plastic bottles instead of throwing them away. If you want to know more about what we do, you can contact us here.
And this really brings, so with all this excitement of this being working, we got quite interesting how this could be potentially deployed with real-world waste. And at that time, when we started brainstorming about this, we were in lockdowns, of course, because of the pandemic. And we had to wait patiently until those lockdowns were lifted. And the first trip, the first excursion we did after the pandemic was actually to our local waste recycler. That's the Water Beach Amy waste recycling facility. It's Thalia now. You may know recap from your bins, and we looked at their waste. And that's quite distinct what we did here and from many of my colleagues, because when I talked to my colleagues, their first trip abroad was to a nice island, to the Canary for a conference, but we went actually to our local waste recycler. And I'm very happy we did, because we could really inspect a lot of the plastic waste. So this is my photo reforming group at the time. And we looked at this large mountain of plastic waste being generated in Cambridge over a weekend. I was personally not so surprised about the scale. It was very unclear to me. I just expected a very large mountain of some sort. But what was quite interesting actually, when we looked into the waste, there was a lot of waste you would not expect there. A lot of PET, for example, or a lot of waste we are being told can be easily recycled. But lots of those plastics is actually not recycled, and it's often the case because it's either mixed waste composition or mixed plastic composition or contaminated plastic of any sort. So we are throwing away a lot of plastic. And indeed, if you look at the numbers, the number of recycled plastic is still only a few percent. We burn maybe 20, 30%, and the rest still goes to landfill somewhere. So, and this was really interesting to us. So we looked at this unrecyclable waste, and we realized there's something we can do. And this was a time when we actually teamed up with the Department of Biochemistry, with the group of Professor Florian Hohlfelder. And from there, a startup that takes care of this. So Jack Gu is the CEO of this startup. He also comes from biochemistry, and you see in the audience, I believe, somewhere. Jack, hi. And I look after the scientific aspect, and Arthur was our first scientist, and we found there's actually something we can potentially do to address this problem. And what we do since 2024 last year is we look at waste that cannot be recycled, and then come in with the technical term would be chemoenzymatic photoreforming, using biological catalysts and synthetic catalysts in tandem to actually convert this plastic waste into something useful. So what we can do is use renewable energy, make hydrogen, clean hydrogen, again, that can be used in a fuel cell. We can make key components for organic chemistry, and also some of the monomers we can just isolate and in principle convert back into virgin plastics. This essentially solves the problem of downcycling of PET recycling, because as you may know, you can only recycle it maybe 2-3 times, then it loses its transparency and it's just being burned off. So you really want to deconstruct it and reconstruct on occasions to make new plastics. And that's also why I would really like to invite you to help us. We have done this at a small scale, and now we have received quite generous funding from Cambridge Enterprise here through their TIF project to actually demonstrate a larger scale conversion of our process. So our ambition is to convert 1 kilogram of plastic waste into hydrogen, but it turns out we don't have enough PET water bottles. So if you have PET water bottles, and I see a few, please empty and look for our bins outside. You can help us making clean hydrogen with your waste, and also make sure we can actually get on with our research quicker. We do not want to go into a supermarket and buy plastic bottles to actually then convert them into hydrogen. And what we will do with your waste is the following. This is Chan Wu. He's either at the display cabinet or just in the back here. He will take your plastic bottles. He will cut them down and put them into our newly installed shredder. He should not put his hand in there, but then we will extrude them, then we will shred them back again, and then we will put them into one of our bioreactors that you can see here, where we take biological catalysts to deconstruct them completely, make soluble products, and that's the job from Irina. And then essentially we will add them and feed them into our large-scale solar reactors to make hydrogen. So please support us with your PET, and you can also make sure you support scientific research here in the chemistry department. And what we would like to do over the summer now to demonstrate how much hydrogen we can actually produce from at a 1 kilogram scale of plastic waste. And with this information, we will analyze it. We will look at it at environmental impact. We will look at cost, potential profit margins, and then decide if we pursue this line of research and really scale further, or if we take a different approach. So it will be extremely informative for us, and with all this information should be available by end of the year. And if you return for the next Cambridge Festival in March 2026, I will tell you the results, what happened with your PET plastic bottle. And again, of course, we want to make hydrogen here. Okay, that's really what I wanted to share with you. So our vision is to build a sustainable green economy from waste, from carbon dioxide, biomass, and plastics. We see these 3 ingredients truly as a resource. And I think that in the future, people will use waste plastics as we use oil today. So in fact, it will be of high value. And we want to be quite early of developing those technologies. And we believe in solar because solar energy simply is becoming, or is already, the cheapest energy form on the planet. And here you can really see the circularity. The 3 ingredients go into our solar reforming processes. We make sustainable fuels and chemicals. We use them circularly. We get waste, and the waste just is feed back in there. So moving away from a linear to a truly circular economy. And what we would like to do here in the chemistry department is really take this further build upon this initial results and state of the art and really create a Cambridge Circular Chemistry Center in the next couple of years. So the idea is to really make a significant contribution from the transition from a petrochemical to a net zero industry, and again contribute to defossilize the industry and build an economy from sustainable ingredients. And that's what I wanted to share. I'm really extremely grateful to my team. Everything I've been showing you today was done by them. So I'm really, really happy and privileged that they're part of the team here. Of course, all the funding sources, all the Walters Kundert Trust who is supporting the Open Day in particular. Thanks for the attention. I'm happy to take a few questions, and afterwards we can discuss in more detail after the Q&A. Thank you very much.
It's fantastic stuff, right? For us in the scientific community, hearing a lecture like this or hearing Erwin talking about his science is the scientific equivalent of going to a Taylor Swift concert, right? A real, genuine enthusiasm, because most of us in the lab are trying to do something which is important. Sometimes we get buried in fundamental research, and it really does matter. But sometimes when we look at someone taking fundamental science and maximizing the impact, that's fantastic science. So we really, really hope you enjoy that. I mean, Erwin's right, we've got a couple of minutes, but what may be more exciting for you afterwards is up to come and talk to him or some of the team. And the videos, by the way, the lovely thing about the group is not only they're doing great science, but they take communicating the science seriously. So if you do go to Erwin's website or via the department website, you can see most of these videos. And the Lego clip has become part of Cambridge folklore here, right? It's fantastic. So if the older amongst you don't know how to do that, ask your kids to go to Google and find this. Any questions for Erwin?
Yes, please.
Do you have any comparison in terms of efficiency of your reactor compared to maybe a solar panel?
Yes, oh, absolutely. Thanks a lot for the question. I did not go into any technicalities, but if you take a conventional silicon solar panel, you have efficiencies of about 22%, so 20 to 25%. In our reactors, it depends a lot. I would say it varies generally from below 1% to maybe 5%. That's something we can reach at the moment, but our key goal is in the next couple of years to demonstrate actually superior performance to solar cells. And goal, yeah, I'm not making any promises. But I think the one way to do this is if you look at the solar cell, we always have to think that they work, of course, with the full solar spectrum. So there's a part of the UV light, the high energy light, the visible light that we see, and the infrared light, which is heat. Solar panels are very, very good of using the visible and possibly the UV light and almost maximize the conversion into electricity. They cannot use the infrared light, the heat. But the heat component is 50% of all the energy in solar energy. So, and this heat is actually bad for a solar cell, because if you heat the solar cell, the efficiency goes down. But heat is very good for chemistry or catalysis. So what we try to do is integrate in our devices heat management that we can actually go beyond solar cell efficiencies. That's a concept we have demonstrated some fundamental aspects already, and we're really focusing at the moment. So I think your question is spot on. Ultimately, for this to be commercially deployed, I don't think we need to be better than a solar cell, but we should not be far away, right? Because you can also hook up a photovoltaic panel to an electrolyzer, for example. Yes, please. Oh.
Can you use a conventional solar panel to heat your reactor?
To make electricity and use the electricity to heat?
To then heat your reactor to make it more.
You could, but this would be quite inefficient, because then from electricity to heat, you have a very significant energy loss there. You could do it, but that's something, I think it would be punitive to do that. There was a question here? Yeah. Ah. This depends on, well, we are trying, we're in the very early stage. I think we have to be realistic. So I will not make you a promise, and neither do I believe this will happen in the next 5 years. And the reason simply is because the scale-up demand is so massive. So, you know, at the moment, our goal is, let's say, to go to 1 kilogram, but we have to go to hundreds of tons until you really make a dent. And even if we troubleshoot all the basic science issues effectively, just to scale up the engineering, it takes a lot of time. So for example, I've been in touch with the major energy company in Austria, my home country, And they are developing, of course, also sustainable plastic thermal processes. And for them, money is no issue, but just to go to a scaled reactor where they go from a few kilos to a ton, I mean, it costs 50 million and it took them 10 years. It just takes time, but we have to get started. So certainly our ambition is in 9 years, because actually I got funding for this, that there's something meaningful in deployment somewhere. But we will probably watch out for a niche market. So we do not want to go into competition with the current fossil energy industry, but do something, for example, where you need to operate in a remote setting where there's no central grid and actually start deploying technology there.
Talking about being realistic, I was struck by the energy mix and the rapid change that the economists perhaps wishfully think
it's
going to happen. What do you think of that?
So things can go very quickly. So yes, it looks dramatic. I entirely agree. So also this was a fast transition scenario. So this particular scenario was based on meeting the 1.5 or 2 degrees targets. Yeah. So of course, if we overshoot and just take the risk, then the transition can be slower. But in order to meet those milestones or these targets by 2050, that's what has to happen. I think I would not be surprised. I mean, also the plot started from 1960, so we're not talking everything changing in a few years, but maybe 20, 25 years. I think it's possible. From the moment, really, I think there's a fair competition between energy systems, and solar is cheaper. I think this will ultimately win. It's just a question of the lobbies as well that are.
It was a long scale, but it did show.
No, a huge transition. Yeah. So I don't know is the answer, but it better does change in a positive way. But again, I think it's very exciting, especially for the younger people in the audience, because this provides huge opportunities, right? All the jobs will be there, and there's huge space to innovate. In fact, I'm an excited chemist, but if you're a physicist, engineer, whatever you do, tap into this. It's going to be a fantastic space to play in. Maybe last question, yes?
Do you think it's deployable in the UK?
So I always say the UK is the real tough test. If it works in the UK, it works everywhere. But on a more serious note, I think it doesn't really matter where it's deployed, right? The kind of what we need to do is to develop it. And even if we build it in the UK, we can export it, right? So I would agree. We know from a fuel production point of view, if you put the installation somewhere in the UK versus southern Spain, we probably get half fuel there than versus southern Spain. Yeah. So it's not a huge difference, but it's still 50 or double. Yeah. On the other hand, you can also argue the seasonal variations of solar energy in the UK are much more severe than closer to the equator. So if you really think about seasonal energy storage, and you have this long summer days effectively, and then store the fuel for winter use, then actually the consideration flips around completely, and you may say the closer you are to the poles, the better is your deployment. And that's just something we don't quite understand yet. So yes, just from a pure efficiency production point of view, you want to be close to, or you want to be in a sunny country, but I can also see niches in the UK.
Very just one question.
Yeah.
It's temperature. What temperature helps more, as you said?
Yeah.
Compared to PV, it's actually positive versus negative. So the hotter it is.
Yes, that's what we're exploring at the moment. In principle, yes. So for example, with heat gradients, we can just add, it's a bit technical, but additional voltage into our devices, and this increases performance. So there are a lot of ways for us how we can use heat in a beneficial way. And also the catalysts usually turn over faster and operate faster under higher temperature. That's what we want to explore as a big advantage of our technology versus conventional approaches.
Okay, well, enjoy the rest of the day. Thank you for making the time to come. Just one more time, Chief, we just to thank Erwin for the excellent talk, and he will be around afterwards, and the team are around to answer questions.
Thank you.